What comes to your mind when you hear the word chemistry and chemicals? Possibly some conjuring images of explosions, some toxic and hazardous substances, poison, acids, periodic table, some difficult chemical formulas. Or some people, some of you might have chemophobia, fear of chemistry, because you might have struggled during your school and college life with the chemistry course. But if you'll ask me, being a chemist, what chemistry and chemicals are, or how do I feel about them, then I have to show you my molecule. Okay, this is one of the molecules that I made during my research stay at Nottingham University. In this picture, you are looking at a molecule. For you, these might just be some sticks and balls sticking together in a random fashion. But if you'll ask me what I can see in this structure, then I can see architecture, design, beauty, colors. The person responsible for making these molecules is known as synthetic organic chemist. But I call her an artist, because it's completely a creative work, how you join the atoms of carbon, nitrogen, oxygen, hydrogen in a very particular manner and make a molecule. The first ever organic molecule was made in 1828 by Bowler, and that was urea, about 200 years ago. Since then, there are more than 30 million organic molecules have been synthesized or discovered. But you would be asking where these molecules are. Well, for that, I would take a little moment of yours to draw your attention and just imagine your life in a hot summer day without air conditioning or without refrigeration. Imagine your entire life without medicines. Imagine a day without these colorful clothes. Or for all the beautiful ladies sitting here, imagine one day of your life without cosmetics. Well, all these products have organic molecules as essential component of their structure. Essential component because for refrigeration and air conditioning, you need coolant gases, which are organic molecules. Pigments and dyes, they are the reason why cosmetics and textiles are colorful. Above all, medicines are all synthetic molecules. And it's that art, that architecture which is making these molecules. These are just to name a few of them. But if you'll ask me, I see molecules everywhere in the surrounding. Well, medicinal molecules are very important because they change the face of the world. They had the strongest impact on society and on mankind. The first ever synthetic medicinal drug was aspirin ages ago, and even up till now, it's an essential part of it's found in every house. If you talk about penicillin, the very first antibiotic which saved millions of lives so far, and which saved a lot of lives during World War II. Quinine, very well-known anti-malarial drug, or Taxol, anti-cancer drug. Just to name a few of them, they have saved many, many lives. Now, interestingly, all these molecules that I've told, and many more, they are actually being produced in nature, either plants, animals, or microorganisms. Extracted from there, found to have these activities, and then made in the lab. Well, an obvious question coming to your mind is, if nature is making them, what's the job of this artist or synthetic organic chemist to make them in the lab? The reason is that nature has its own way of making things. We can't teach nature. We can just learn from nature. Nature has its own time frame, and nature has its own quantities to make these compounds. Just to give you one example, Taxol, very famous anti-cancer drug, it is produced in yew tree, and yew tree takes 30 years to mature. Imagine a cancer patient waiting 30 years on the bed for the yew tree to grow, and then extracted the Taxol from there in very little amounts. Of course, would he survive? No, we don't know. It's a long time. So that's how the duty is assigned to the synthetic organic chemists. When I started my journey of making molecules, during my stay, when I went to Nottingham University for my PhD studies, I chose to work on 3 medicinal molecules as well, because of my inspiration from these molecules. They were symbodiacetal, a potential anti-malarial agent, which I managed to synthesize in 10 steps and published afterwards. Eritazone, which I managed to synthesize in 5 steps, again a potential anti-malarial agent, 5 steps. Dihypoestroxoid, which is a potential anti-cancer agent, I managed to go 22 steps towards it. Well, my love and affection towards these molecules rewarded me with Leslie Crombie Prize at University of Nottingham, which is awarded to the best PhD student at the research day, at their final research day. I have told you all the good sides of it, but I haven't told you about the struggles and the challenges that I faced in those 22 steps, 10 steps, and 5-step synthesis. While making these molecules, there are a lot of challenges that we face. It's not an easy job at all. It's an art, but not an easy art. Well, again, a question might be arising in your mind. My 3 molecules were also coming from nature, from plants. A question might be arising in your mind that if nature is making them, then mimic the process and take inspiration from nature. Yes, we do take inspiration from nature, but nature again has its own way of doing things. For example, most of the reactions in nature take place in water. In our body, a lot of reactions are taking place right now at the moment, in all of you and in me as well, but they are happening in water. So water is a solvent or a media for that reactions. Nature doesn't use high temperature or high pressure. Reactions happen at the ambient conditions. And nature have magic things called enzymes, which speed up a reaction. When we try to mimic the same process in the labs, then very little reactions take place in water, if I'm honest. We have to use high temperature, we have to use high pressure, and we have to use catalysts, which are again chemicals, right? So in all that process of making these good things, good in every walk of life, in so many industries, intentionally or unintentionally, we are actually producing a lot of other things which are hazardous and toxic to the environment and to mankind. Give you one example, and sometimes the product itself, not the process, but the product itself is bad. How come? CFCs are chlorofluorocarbons, which are used as a coolant gas in refrigeration, which were used for 50 years as coolant gas in refrigerations, but then they were completely banned in 1987 by Montreal Protocol. Why they were banned? Apparently they were good. Apparently they were not harming human health, but they actually caused a mass destruction in the ozone layer. They made a big hole in the ozone layer, a layer which protects the whole planet from harmful UV radiations. So actually it not only harmed the human life, but it also harmed plant life, animal life, in general, the whole planet. So that was the case of unintentional loss, unintentional damage that scientists has made to the mankind, if he knew that this is CFC going to happen, this is what CFCs will do to the ozone layer, he or she wouldn't have made that. It was made by Thomas Midgley. Well, where is the solution? How should we make things? How should we make processes which are not harmful to the environment? It's not one thing, I must say. It's a combination of 12 principles that were initially Paul Anastas and John Werner. John Werner, also named as father of green chemistry. He proposed these 12 principles that if followed in true spirit, we can make things which are not harmful to the planet. We can make things, we should make things which are economically viable. We should make things which are competent enough to compete with the existing products. Some of the principles I would just tell you, just few. We need to prevent waste. We need to work on energy efficient processes. We need to use renewable resources as starting material. We need to prevent pollution. So, without going into further detail, I would tell you my inspiration of working towards green chemistry. It was the end of my PhD studies. I was writing up my thesis when, in 2012, GlaxoSmithKline, a big pharmaceutical company, a lot of you might already know, they actually funded a massive amount to University of Nottingham, 15.3 million pounds, were invested to construct green and sustainable chemistry laboratories. Because at that time, 2012, GSK realized that if we have to work on green chemistry principles, then we have to invest in academia, because these are the people who are making these products. If they make it right in the first place, then the same technology will be transferred to industry, and that would be right for the rest of the life, right? It has to be corrected in the first place. You can't, because molecules are just molecules. They are not like human. we can grow a child and tame them to behave well. We can grow molecules, but we can't tame them to behave well. It's the person who is making those molecules responsible for everything. Well, the second inspiration was International Green and Sustainable Chemistry Conference, 6th international conference that was at that time hosted by University of Nottingham. I got a chance to work in the organizing committee of that conference, and I got a chance to meet with mentors and peers of green chemistry, and I also got a chance to sit with in discussion forums with policymakers. And the one thing that they were emphasizing a lot over there was prevention of waste by solvents, because solvents, as I said, water solvent in us, the same way methanol, ethanol, diethyl ether acetone, benzene, we use these solvents which are volatile, they go in the atmosphere, flammable, catch fire. Some of them are carcinogenic, like benzene. A lot of discussion was all around replacing them, because they don't even become the part of the product. They just a part of the process, and at the end they are just waste, right? So a lot of discussion was around replacing them with green solvents. When I came back to Pakistan and started my own research group at Institute of Chemistry, University of the Punjab, what I realized was that in the form of solvents, about 2,000 liters of solvent is coming about every year in chemistry departments. And it's becoming waste at the end, because solvents don't become the part of the product, it's just a part of the process, and they are wasted at the end. So I thought if I could do something towards that first principle to prevent the waste, then that would be the right step forward towards green chemistry. So I chose to work on green solvents, and the one that inspired me, that I'm currently working on, my research group is currently working on, are ionic liquids. Ionic liquids are termed as green solvents because they are molten salts. Why they are considered green? Because they are very polar. They can dissolve many, many, many things in them. They are not volatile. They don't go into the atmosphere. They are not flammable. They don't catch fire. They are very stable thermally and chemically. Above all, the most interesting thing, they are recyclable. You can recycle them multiple times. So my research group is currently working on synthesis and applications of ionic liquids. It has a wide arena of applications. I would just tell you two of them at the moment. One in synthesis and second in biomass processing. So the synthesis, like making molecules, which I called an art. In the beginning, initially, I collaborated with the Institute of Agriculture Sciences to make some molecules for use in pesticides. Like human body become resistant to antibiotics and there is need to make new and new antibiotics all the time, the same way plants get resistant to existing pesticides. There is need to make new and new pesticides all the time. Keeping that in mind, I chose to work on different variants of coumarines. They are, again, a class of compound. I chose to make different derivatives of that. And for that, the traditional processes that were using, again, the solvents, traditional solvents, which are flammable and all that, which I've already told you. They were using high temperature. The process was not energy efficient. And they were using catalysts. So we replaced the traditional method with ionic liquids. The novel ionic liquids that we synthesized, we used them for making coumarines. How they work? They work both as solvent and as catalyst. So we don't have to put additional catalyst into them. The reaction took place at room temperature, so we didn't have to put high temperature in that. And the solvent and catalyst, both were ionic liquids. We recycled them up to 10 times. So I thought that was kind of the first success towards that aim that I've set for myself to work on green chemistry. We then made a large number of derivatives, and some of them could potentially be pesticides in future because they showed good antifungal activity. The second application I would tell is biomass processing. So before going to biomass, I would just draw your little attention towards smog issue. Smog issue, I think all of you might be aware. It's a very common issue, especially in this weather. When smoke and fog, they combine together, it makes smoke. How smoke is generated in the first place? What are the causes of smoke? Of course, smoke from automobiles, which is difficult to stop. The other thing, burning of agriculture waste. About 90,000 kilotons of agricultural waste is generated every year in Pakistan, and that's the data taken from 2014. The situation might be worse now. And that's burnt ruthlessly to create all that smoke, which then ends up in making smog. I thought, what if we, rather burning that waste, we could convert that waste into a useful substances. So we processed that biomass, and we converted them into bioethanol. We converted them into phenolic compounds and HMF and levulinic acid. So that is, I would say, my first initial step towards a long, long journey that I have to go on. My 3 PhD students and 2 MPhil students are currently working on that project because that excites me a lot. If you could convert the waste into useful stuff, that's the best thing you can do. And the waste, which is renewable and sustainable. Then, at the end, I would like to draw a little attention of the society towards, or some of my suggestions for working towards sustainability and green chemistry. First, for academia. So according to Einstein, you can't solve a problem with the same level of understanding which created that problem, right? You need to have a higher level. You need to have more knowledge, you have to be more innovative and creative to design things. Because actually academia or research labs are the ones which are making these molecules. So as GSK considered it right at that time, that the problem has to be fixed over there, and then industry would adopt it. So the same way, my suggestion is that a green chemistry course should be an essential part of all the chemistry degrees, chemical engineering degrees, and environmental degrees, so that the students know the toxicology and environmental impact of these molecules, what these molecules are going to do with the society, how would they end up in the environment. The next thing for R&D organizations, funding agencies, higher education commission, that we need to invest, like GSK invested in University of Nottingham. Funding agencies and R&D need to invest in academia to such processes which deal with renewable, sustainable materials, green chemistry practices, so that we can go towards sustainable economy. The last thing I would like to draw the attention of the general people, society, that we need to ponder upon three things: recycling things, reusing them, and reducing the waste in the first place. Because at the end of the day, it is our planet and we have to save it. Thank you.